So d equal 2 first. D equal 2 first. Because this thing about Chern-Simons forms, well, they are mostly important in 3 dimensions, we will see, because in 3 dimensions, in odd dimensions, the integral of the Chern-Simons form is invariant. It's an interesting topological action. It's called Chern-Simons action. Because the variation C is not invariant under a local Lorentz transformation, but its variation is a total derivative. So if you integrate C in 3 dimensions, because it's a 3 form, then you get something sort of action. It's called topological because it doesn't really propagate any physical degrees of freedom. But let's do this in 2 dimensions, where apart from the coefficient which depends also on, as far as the sign is concerned, on whether you are on a Riemann or Minkowski manifold or Lorentz manifold. So on a Riemann manifold, that is. So in 2 dimensions, you have an epsilon tensor which has 2 indices, and the curvature RAB has 2 indices, and it is already a 2 form. So this is the integral of a 2 form. By the way, this gives the what would be also the Hilbert action, which means that in 2 dimensions the Hilbert action doesn't propagate any degree of freedom because it's a total derivative. And well, yes, we can show that by doing the usual stuff. R, A, B, M, N, E, M, E, N divided by 2. So that is simple. EM, EN, again, will be equal to so R, A, B, M, N. EM, EN will again be equal to the determinant d2x now. This you can do it immediately by writing EM, if you want, as EM mu dx mu. 2 dimensions, everything is much simpler. And then you have EMN, epsilon MN, epsilon AB. Epsilon epsilon is, I don't remember if I use the sign here for Lorentzian manifold or Riemann manifold, because the Riemann surfaces are Riemann manifolds, and so we'll check it in the end because I have the correct sign in the other form. Actually, I hope so. Should be this. Epsilon epsilon again is a determinant of deltas. So let's say Riemann surfaces. So we will check the sign. Epsilon epsilon, so it's a determinant with a plus sign if we are case of Riemann manifold. -1 divided by 16 pi R A B Mn and then you have delta MA delta NB delta NB minus delta MB delta NA. So this is MANB, this is R. And there was E, and there was D2x. So you have twice the same thing, minus 1 divided by 8 pi integral D2x square root of minus GR. So I remember that this should be plus 1 and with 4 pi in the other form, so we have to multiply everything by minus 2. For 4 and 8. At the same time, this is the integral of a total derivative. So let's go back to this form and we replace R AB with its definition. And this is just 1 divided by 4 pi integral of m. The first one, you see, is a total derivative. But again, it is a total derivative of something that is built with the spin connection omega. So that's a Chern-Simons form in 2 dimensions, omega AB, epsilon AB. And the other one is 0. This term, that term gives nothing. So that is omega AC, omega C, B, epsilon AB. That is 0. Actually, without the integral, that is just 0. Why? Because epsilon AB can only be epsilon 1, 2 or epsilon 2, 1. So A and B can be only 1, 2 minus 2, 1. But now we use, here we have to use the metric compatibility, which was already in the assumptions of the Palatini action. Actually, I don't think we need to use the torsionless condition. No. But the metric compatibility, yes. Which I recall implies that the spin connection is antisymmetric. And then you see there is not much you can do here because the two indices C must be equal, but since omega is antisymmetric, they must also be different. So if this is 1, this must be 2. If this is 2, this must be 1. So they cannot be equal. If this is 2, this must be 1. And if this is 1, this must be 2. So let's say this is 1, 2. This should be 1, 2, 1, 1, 2. Doesn't make any sense. There is not even room for building such an object in 2 dimensions. So in 2 dimensions there is no gravity. No graviton, no gravity at all. In 3 dimensions, by the way, there is no gravity as well, but for another reason. And the first dimension where there is gravity is 4. In 3 dimensions, you can show that the Hilbert action is a Chern-Simons action. precisely itself. It's not a total derivative, but it's like the integral, not this Chern-Simons, however, it's another one. But anyway, now d equals 4. So once we will have clarified this and introduce another important tensor in 4 dimensions, which has to do with quadratic terms, which is the Weil tensor, which we will do the next time, I think, we will have already the complete action of quantum gravity. We will not know yet how to use it, how to quantize it. And that will be actually the issue, because the classical action is one thing. It will not even be the final classical action, by the way, because the quantization will involve a long process, and strictly speaking, these corrections, which are quadratic, are not acceptable. Not classically, and well, at the quantum level they are acceptable, but they will be treated in a certain way that will even modify the classical action. So the classical action will not be the classical action we will write. So we will explain why these terms are naively not acceptable. And the reason you might already see it is that the Lagrangian written that way does not depend only on positions and velocities, but also position, velocities, acceleration. There are too many derivatives here. Too many derivatives. So it's not like having a Cauchy problem. But we will do it step by step. So for the moment, let's just do another exercise, with long exercise in manipulating indices, and hopefully this will get you accustomed with these things enough to do them very quickly. I'm doing the calculations in detail also because otherwise the program of this course will be too much. So this way I think we can view these calculations done here as exercises. Which dilute a little bit the topics. So let's write this. At any rate, these are things that once in your life you should see, and probably this is the only one for many. So we have to replace the curvature with their definitions. And then we will have Wirth terms. The first one, d omega, is clearly a total derivative. That's easy. The second one is not so clearly a total derivative. There are two terms, omega, d omega, but they are. And the fourth one, as like in 2 dimensions, omega, is 0. So let's write this as integral of m. The first one can be written as a total derivative. the exterior as an exterior derivative, yes. Because when you act dx on omega, you get d omega. When dx on d omega, you get 0 because it's nilpotent. So the first one is okay. The other two, as usual, give the same contribution because you have omega d omega or d omega, but there are two forms. Omega is a two form, d omega is a two form, so you can exchange them paying no price, and it's like exchanging the couple of indices AB with the couple CD. So you have 2 integral over m d omega AB omega CD, let's say omega C F omega F D epsilon ABCD. And the last one is 0. So omega AF, omega FB, omega CG, omega GD, epsilon ABCD. So let's consider first, so this will drop. Why? Let us write it here. One trick is to write 1 omega, the first one, as follows. Let me write this omega here by raising indices actually. So let me do that. Omega AF I can write as epsilon AF M N epsilon M N something PQ omega PQ. Why? Well, because these are two epsilons with two contracted indices. So those two epsilons just give minus 2 delta minus 2 delta AP delta FQ minus delta AQ delta FP. And those two give omega AF both, so you have minus 4 omega AF times minus 1 over 4, which is okay. And then you copy the rest. Why is that useful? Because now you have 3 epsilon tensors, and you can play a trick with 2 of them, which are those that have one contracted index. Those two have one contracted index. Okay, so you can write this as minus 1 over 4. You copy the remaining epsilon tensor. You copy everything else. Times the other two epsilon tensors. So actually you have a minus sign. We have to be careful because in the end we want to show that this is 0. So there is a minus sign because epsilon epsilon in Lorentzian manifolds give minus sign. And then you have delta, so you are contracting A, B, C, D, A, F, M, N, F, M, N, F, M, N, F, M, N, A, B, C, A, B, C, A, B, C. So it's anti-symmetric in M and N, which means that we can compute it maybe this along this column. So M and N will give twice the same contribution, and then yes. So there will be, so if you compute along the column, the other two columns are just obtained by exchanging M and N. So they give it factor 2, and there is one contribution that doesn't give anything, delta BF, because delta BF will contract the indices of the same omega, and we are using always the metric compatibility. So only two contributions, not that long in the end. So delta FA, two contributions which double, there are four contributions, but then only two, and there is a factor 2. So 1/2 times delta FA, which means that this is an A. So we have epsilon, omega, omega, omega. Delta FA, delta MB, delta NC. Epsilon M N P Q, delta FA, delta MB, e delta FA, delta MB e delta NC. Omega PQ, there are four omegas, so I forgot one. Omega CG, omega GD. CG, omega GD. So omega PQ remains omega PQ. Omega FB becomes omega AM. Omega CG becomes omega NG. And the other one is omega GD. Totally wrong, because the contracted index is A and the indices here are B, C, and D. So we have to start over. And we will see if this one is the one that disappears, or there should be one that disappears, but maybe it's not this one. So FMN, 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 and the other indices are B, C, and D. B, C, D, B, C, and D. Let's see if there is something that disappears. BF, yes, the first one. This disappears because you contract that thing. Okay, so the first contribution is calculating this one along this column. Delta FC with the minus sign. Delta FC means that here we have omega CB, omega CG. Delta FC, delta MB, so yes, this was M, and delta ND. Okay. The two will give the same contributions, so. But anyway, delta FD delta FD means, okay, FD, whatever. Delta FD, delta MB, delta NC. MB NC, delta NC, and the last one is omega GD, delta FB we said, so. Okay, those two. Now let's check this one. Let's move the form, that form, to the right. It's a commutation between one form and two one forms, so we do not get any minus sign. It's just to order the indices, because here you see you have NG, GF, FM. So the second term is what? Omega, 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 NGGF, FM, NM. And the first term will be the same, actually. So it's just a matter to recognize that the first one gives the same. Let me check again the order. N, G, G, F, F, M. Okay. So N, M, yes. But the first one seems to be the same, but there is a minus. Let's check.
The minus sign is plus, I think, because the determinant of the delta is minus.
Where?
Lorentzian, when you compute the epsilon times epsilon, you put the determinant without the minus, because you're in Lorentzian manifold.
No, here we are, yes, here we are in a Lorentzian manifold. So there is a minus, that's why I changed this.
But then you did not change the sign on the other page, I think.
Okay, let's see. So here there was a minus for the first, because it's in second place, first contribution, delta FC omega C B omega CG omega GN. Okay. And then there is this one, which should be with plus delta FD delta FD delta MB again, and delta ND. So DM or FM, C is N, NG. Seems okay to me. But there is a problem here, something that doesn't turn out to be right, apparently, because well, let's check. NGGF-FM, this is in order, so it gives NM. But the first one, you see, you have CGGN. Here, you have to exchange those two indices to have MC. And then you have MC, that's a minus sign. MCCGGN. But then you have minus minus, which is plus, like here, but not NM, but MN. So apparently there is a minus sign problem, because you get 0 directly. Instead, I did not expect to have 0 at this level. There was another manipulation to prove that this was 0. But we can check it again here. So, apart from the overall sign in the end doesn't really matter. So we can start from here. Epsilon Mn PQ, omega PQ, omega FB, omega CG, omega GD. And then there is a determinant FMN, FMN, BCD, 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 BCD. So we can start from here, because even if there were or not a wrong sign, overall doesn't really matter. We want to show that this is 0. Okay? So delta FB gives nothing, so this gives nothing. So we move to the second one, delta FC, which means that this is a C, and we have a minus. So minus 1 over 2 epsilon Mn PQ omega PQ. Omega delta FB becomes CB, CB, and B becomes M, and D becomes N. So we have omega CM, omega CG, omega GN. That's okay. Plus delta FD, so omega GF, delta MB, delta NC, MB and NC. That's it. Okay, this is okay. So when you move this there, you get NGGFFM, omega, 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 NM. And here, you do not need to move anything. but you just need to exchange those two indices, which means minus sign. But then you have omega, 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 mn. So apparently the first one, mn, and the second one, after exchanging that, omega, 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 and m. That is 0. Just a moment here. Yes. Yeah, it's corresponds to what I have. So I was prepared to show that even this single contribution is 0, but apparently they cancel out. To find a mistake, tell me.
Sorry, another thing. In the first line, you have omega Cm multiplied by omega C. So right to write the multiplication, we should have omega MC maybe. So we should raise the index C and exchange M and C, so we have minus sign.
Minus sign. And then that you have both pluses. So you have plus here. But then you have Mn, omega, omega, omega. So you have MCCGGN, so it's product of three matrices, and with M to the right, to the left, and N to the right. Instead down, it seems that you have NM, because this remains to the left, NGGF. Or what could we do? Let's try another thing. You can exchange this with that, so you have MF. Then you have to exchange these two, and to exchange this with G, and this with that. So you have one minus sign, one minus sign, one minus sign, and another minus sign. And yes, that would give what I get there. So let's do it. Apparently, the path I chose last year was a little bit too long, but it's 0. So let's write this one in a different way. Apparently, it can be written as the opposite of itself. So let's do it. Both things apparently. Let's see. So if we take this and move it to the right hand side, we have NGGFFM, and that is it doesn't even need to be, can remove that. That is equal to omega, 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 NM. Mhm. But if instead we exchange those two, we have a minus omega mf. We exchange those two, minus omega gn. And then we have another minus omega fg. At this point, we exchange those two. That is another minus, so you have omega mf, omega fg, omega gn. But that is omega 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 mn. Actually, now that I think there is a reason why it's so, we can explain that. So this is symmetric in m and n, so you get 0. That's the quickest way to prove that that thing is 0. Maybe for today we stop here. The point is that this is an antisymmetric matrix, omega. When you take the cube of an antisymmetric matrix, you get an antisymmetric matrix. But this is a cube of a form, so there is an extra minus because it's omega, 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 a form, so it becomes symmetric. It's a cube of an antisymmetric matrix that's also a form, and any time you exchange those two, you get minus signs. So in the end, you get a symmetric matrix. And because it is symmetric, that kills the contribution. So we can stop here for today. The remaining term we will show next time.